Hello guys, welcome back to my video lecture series on the Black-Scholes derivation. This is going to be video 12, or the second video of part 2 of this video lecture series. And in the previous video, we were discussing the necessity to find dV as a function of our stock price and time. So essentially, what this is v as a function of two parameters s and t, which we can think of as f of x, y. It resembles the same nature, and obviously we want to find the differential of this. So how do we do that? So before we get to this step, for a multivariable differential approximation, we want to discuss representing just a single variable function, f of x. And one of the biggest ways, or most useful ways to do this, is using a Taylor series approximation. And that looks like this, as follows. So in the mathematical literature, if you've taken calculus 2 or integral calculus, towards the end, you'll learn about how to approximate a function f of x, and that would be equal to the infinite series from an n is equal to 0 to infinity of 1 over n squared times, or not partial derivative, let's do derivative for now, dnf dx n times x minus a, and a is a free parameter to the power of n. So without the infinite series form, I can write it as such. I can write it as f of a plus df dx, and obviously f is a function of x, right? But in this case, I'll just write it as df, just for simplicity's sake. Times x minus a, that's going to be my essentially second term, and then my third term is going to be d squared f over dx squared times x minus a squared, all times 1 over 2 factorial, which is just 2. And then I'll add that with my fourth term, which is going to be d cubed f dx cubed x minus a cubed times 1 over 3 factorial, which is just 1 over 6, and then I'll add this an infinite amount of times. And obviously, this will go up until d to the nth derivative of f dx n, x minus a to the power of n times 1 over n factorial. And this infinite series essentially will give us a function of f of x. It's essentially the same thing. These two representations are equal. Now that we have this, I'm going to do something that isn't typically shown in a calculus class. I want to bring f of a over to this side. So essentially what I'll have is f of x minus f of a is going to be equal to df dx x minus a plus, I'll take the 1/2 over here, d squared f dx squared, or the second derivative, times x minus a squared plus, and I'll write the third term, so that's to show the Taylor expansion. 1 over 3 factorial is 1 over 6, and then d cubed f dx cubed times x minus a cubed, and so on and so forth, right? Now I want to do something interesting here. I want to take all of this and apply a limit to it. I want to say the limit as a approaches x. And when we do that, there's a few things I want you guys to note down. The limit as a approaches x of f of x minus f of a is going to be the differential of f Similarly, if we take the limit as a approaches x for this other term that involves a, we would get, as a approaches x, we would get dx. Now, if we make these substitutions, then we would get this following equation. We would get df, and obviously this is a function of x, just to make it clear, is going to be df dx times dx plus 1/2 d squared f dx squared dx squared plus 1 over 6, or 1 over 3 factorial, d cubed f, third derivative of f, dx cubed, and so on and so forth, until we have 1 over n factorial d to the nth times the nth derivative of f times dx n. Cool, so this is what we have right now. And I also want to make another note over here. I have dx, which is essentially going to be equal to 0, but not quite. It's a differential is essentially an infinitesimally small increment or value of x, right? So dx is going to be equal to 0. And I want to say that if we have dx to the power of n such that n is greater than 1, then dx to the power of n is going to be equal to 0. Therefore, this term, and all other terms up until the last term are going to be equal to 0. So we can just cancel all of these out. So essentially, what we have in the end is df, which is a function of x, is going to be the derivative of f of x times dx, which is a true statement. Now I want to focus on this just to foreshadow a little bit. I said when n is greater than 1, then dx to the power of n is greater than 0. Now I want to bring back something we talked about a few videos ago, which is the quadratic variation of Brownian motion. And essentially, what that states is dw squared is equal to dt, or dw is equal to square root of dt, which can also be written as dt to the power of 1/2. And the reason I'm pointing this out is because 1/2 is actually less than 1. So whenever we have a term with dw squared, specifically dw squared, in terms of time, dw squared is not going to be equal to 0, because, as stated before, dw squared is going to be equal to dt. And this is going to be very important when we expand out our differential form for a financial derivative premium price. But before we do that, I'll go over the multivariable Taylor expansion in the next video. More specifically, we covered f of x as a Taylor expansion, and the next thing we need to cover is f of xy as a Taylor expansion, because once we do this, then we can actually find dv as a function of s of t. And we can also incorporate this fact into that to find a full expanded out model of our dv. So in the next video, we'll be talking about the multivariable form of a Taylor expansion.